Hello again and welcome back to the 7th lecture. We are now officially more than halfway through this course. This one is about the Milky Way, and I guess you could argue that the Milky Way also fits into the mini-series of star-forming galaxies, given that the Milky Way is, well, a star-forming galaxy. But you could also argue, which I'm going to do now, that the Milky Way is kind of special because we know so much more about it. And on the other hand, there are things we do not know about it, that it kind of merits its own category. As I have made a little bit of a habit of doing at this point, this one is also split into 3 major parts. The first part is about stars in the Milky Way, the various stellar populations that we can see. The second one is about the Milky Way's metallicity. And the third one is about the multiphase interstellar medium in the Milky Way. But first, let us take a look at the stars, those pretty little creatures. Here we have an observation, or rather a map of stars in the Milky Way. This is not one observation. This is the cumulative observations of the satellite Gaia, which has been continuously observing the Milky Way and its stars over a period of years and slowly building up this absolutely stunning and fantastic map of stars in the Milky Way. We can try and zoom a little bit in here and see the amount of detail that we can see in this galaxy is just absolutely stunning. We can maybe zoom in even a little bit more and see that there are, in fact, just so many stars in this. Okay, the pixel resolution is a little bit so, but you can see, I guess, even now that there are actually resolved stars in all of these parts that we can see here. It is really, really impressive. But this is an optical light. If we take a look at a similar map of the Milky Way in near-infrared light, it looks like this. And I think it is quite interesting to compare these two maps. First off, we can see, especially in the Magellanic Clouds, the difference between the difference between the extended older stellar population and the younger more clumpy stellar population is really noticeable in the Magellanic Clouds. We can also see that there is much less visible dust in the near infrared, as we would expect, given that we have now learned that dust is much less affected by or the other way around, that infrared light is much less affected by dust than optical light is. Going back to our previous map of the Milky Way and its main components, this time we are going to focus on the Milky Way itself and its various stellar components specifically. But this will be things that you have seen before, at least here in the beginning. First, we have the bulge of the Milky Way. The bulge is a few kiloparsec across, and it has a mass of around 2 times 10 to the 10, or about 20 billion solar masses. So even though it is quite small, it has a very large concentration of stars in there, which means that it has a very large stellar mass still. Then we have the disk. We see it here, and we see it over here. The disk has a radius of about 15 kiloparsec, and its stellar mass is about 6 times 10 to the 10 solar masses, so only about 3 times the mass of the bulge. The sun is found at around 8.2 kiloparsecs from the center, and we also mainly find open clusters in the disk. Open clusters are clusters of relatively new formed stars. Clusters that are not massive enough to make these clusters gravitationally bound. So open clusters will not survive for very long, but will over time disperse and mix up with the surrounding stellar population. unlike the more massive globular clusters, which are so massive that they can stay gravitational bound and therefore can survive as independent physical structures in the galaxy. Then we have globular clusters. As I said, these are found in the disk, but mostly in the halo. And there are both metal-rich and metal-poor globular clusters, as we have seen before. The mass of globular clusters, or the mass of a globular cluster, is typically about 10 to the 5 solar masses, but they can grow as large as up to a few times 10 to the 6 solar masses, which is basically the size of small galaxies. The disk has both a thick and a thin component, as I also pointed out in a previous lecture. The thick component has an older stellar population with less gas, which has like a larger, it's more dynamically warm than the thin component, which is very dynamically cold and has very much higher gas content than the thick disk. Stars in the disk, if we look at an HR diagram, we can immediately see, now that we have a well-trained eye from previous sessions, that there is active star formation going on in the disk, as we have a main sequence that is quite conspicuous all the way out to the most massive stellar types. We can also see that there are also older stars that have turned off and up to the red giant branches. This HR diagram is from stars out to a distance of about 100 parsec from the sun, and is taken with the Hipparcos satellite, which was, I don't remember exactly when it flew, but it was in the late 90s or early double zeros. I'm not entirely sure, but this catalog has about 15,000 stars in it. But then along came Gaia and completely and utterly changed the game. You have seen this plot before. It is massive. There is like 4.5 million stars in this figure now, and you can see the same general tendency as before, that we have mixed stellar populations. We have a solid main sequence all the way out to O and B stars, which we only have because there is still ongoing star formation. The density in the disk is given roughly by this one formula that we see here, where RD is what we usually call the radial scale length of the disk. So here S is a specific star type, because the star density changes for various stellar types, as I kind of hinted at before. Older stars have a different scale length or a different scale height than newer stars do. We can see that the Milky Way, the thick disk, has a scale height of around 900 parsec, and the thin disk has a scale height of about 300 parsec. About 15% of stars per square arc second are in the thick disk. So that means that if we take a look from here and down, or square parsec, sorry, if we take a look from here and down and do like the projected surface density of stars, then about 15% of these stars are in the thick disk, even though the thick disk has a 3 times higher scale height. So that should again tell us that the thick disk has a much more thin and fluffy stellar population than the thin disk. The thin disk consists mainly of younger stars. It has a lower velocity dispersion in the up and down direction. It has a higher metallicity, so these are stars that are formed at a later point from gas that has been recycled already and chemically enriched. And it has a low content of alpha elements over over iron. The thick disk consists of older stars, older than about 8 gigayears. It has about twice the velocity dispersion in the up and down direction compared to the thin disk, which is the same basically as saying that it is more dynamically warm than the thin disk. It has a much lower metallicity, sometimes down to a few percent of the solar metallicity, and it is enriched in alpha elements, which means that there's no enrichment from supernova type 1a. So alpha elements are elements that form in stars, where iron forms also a little bit in stars, but mainly in 1a supernovae. So if you have an enhancement of alpha elements, that means you have an younger population that has not yet had a lot of time to form or to set off type 1a supernovae. The thick disk is, again, kinematically and chemically distinct from the thin disk, even though they, to a large extent, occupy the same space. It might mean that it represents a distinct relic from the formation of the Milky Way, or might even be due to infalling satellite galaxies or something like that, or it might simply be an earlier generations of stars that have formed before the majority of the gas in the thin disk had yet been accreted onto the Milky Way. There are many different possible explanations to this question. But it is definitely a fact that they are kinematically and chemically distinct from each other, and that the thick disk is much older than the thin disk when we look at the age of the stellar population there. Then there are stars in the bulge and in the bar. The bulge and the bar contain mainly old stars, even older than in the thick disk. These are more than 10 gigayears old, or they are similar to or older than 10 gigayears. They have a very high velocity dispersion, about 100 kilometers per second, which means that these are dynamically hot. This contains what we call the long bar, which is revealed by the asymmetrical distributions of stars in the center, which you can kind of see here-ish. And it also contains the main bar inside the bulge, which is revealed by detailed kinematic studies. So we have a bar that sits inside the bulge, and then the younger extension, or the longer extension of the bar that also reaches outside of the bulge. Then we have the stars in the halo, and these consist of two main populations. There are the halo stars, and there are the globular clusters. So the halo stars are a diffuse population of old metal poor stars that are like smoothly distributed throughout the entire halo. And then on top of that, we have about 10 to the 9 solar masses in total worth of globular clusters, which each have a mass of around 1,000 to 100,000 solar masses. But as I said, some of the most massive ones of them can actually get even larger than that, and get so large that they can compete with small galaxies in stellar mass. A main difference being that globular clusters rarely have, or do not have, their own dark matter halo, such as small galaxies do. Globular clusters are, as I said before, gravitationally bound, so they are stable structures. They typically have a luminosity of about 10 to the 6 solar luminosities. They can have a very high central density of stars, as much as 10 to the 4 or more solar luminosities per cubic parsec, which is a lot given that there is no more than a handful of stars in this cubic parsec surrounding the sun itself. So try to imagine what the night sky would look like if the sun was located inside of a globular cluster. They also have very small core radii down to a few parsec and very high random speeds of the stars. So they are quite dynamically hot. They do not contain gas. They do not rotate. They have like random orbits, almost like they were miniature versions of elliptical galaxies. Their ages they're all quite old. Their ages are a few gigayear and up to almost as old as the universe itself. They are mostly metal poor, but there are also a few more metal-rich ones, which shows us that those probably have formed at a later point than the metal-poor ones. And the metal-rich globular clusters are more close to the bulge and to the thin disk, which kind of supports that what I just said. Each stellar component has its own distinct velocity dispersion and rotational velocity, which means that you can learn a lot from looking at a plot of these two things against each other. So what we can see here is that, for example, the thin disk has a quite high rotational velocity, but basically no velocity dispersion internally, whereas the halo has basically zero rotational velocity, but a very large span of velocity dispersions. And out in the thin disk, we have kind of an in-between population, which has also almost as high velocity, rotational velocity as the thin disk, and also a good deal larger velocity dispersion than the thin disk itself does. That was it for the first part of this lecture. Thank you for staying with me, and I will see you in the next one. Bye for now.